Oh, okay. So the worksheet 13 is actually going to be assigned to you on your homework check. However, we're going to do a lot of it together. It's actually very challenging. And this is actually not anything I'm going to assess you on, but it's a really good way to synthesize your learning about the graphs of rational functions. So what we're going to do is I'm going to give you a graph, and you're going to come back and find the equation. So I want you to kind of think backwards about what everything means as far as graphing rationals. Let's actually look at number 2. This is a good one for us to look at. I notice a few things about this graph. Let's try to identify them here. My pen will work. There we go. So I see a vertical asymptote at, now it's a little hard to tell because everything's not graphed real accurately, so how about I just go ahead and tell you that this vertical asymptote right here is at x equals -1. And then this vertical asymptote here is at x equals 4. There are no holes in the graph. There is a horizontal asymptote at y equals 20. Good to know, good to know. And then there's some x-intercepts, or there are 2 x-intercepts actually. This one right here, there's an x-intercept at -3, 0. And then there's another x-intercept right here, which is at 2, 0. If for some reason I was going to assess you on this, I would very clearly mark these things, or definitely have someone else graph. Alright, so can you come up with the function? Don't worry about all this limit business. I'm not worried about this today. Let's talk about writing the rational function. How do you find, let's start with, there's no holes, so let's start with the vertical asymptotes. Where in your equation, in your formula, do you see the factors that produce vertical asymptotes? Is that the numerator or the denominator? Is it the coefficient business? Which one is it? It would be the denominator's factors. So if you have a discontinuity at x equals -1 at x equals 4, that means in your denominators you would have had the factors of x plus 1 and x minus 4. So what about, let's talk about the x-intercepts. Again, there's no holes in this graph, so you don't have to worry about anything canceling. Your x-intercepts are found by setting your numerator's factors equal to 0. So in order for you to produce an x-intercept at -3, that means you must have had a factor at x plus 3. And then over here you would have had a factor of x minus 2. So there's just one more clue in this question, and that would be the fact that you have a horizontal asymptote at y equals 20. So in order for you to have a horizontal asymptote at an integer, that means your coefficients, it has to be equal weight, which it is, and your coefficients have to simplify to 20. Well, technically you guys could put anything you want here, but it has to reduce to 20, so your lame teacher is just going to say 20. Yes, you can just magically throw coefficients on when you need them. Cool. Thanks, math. Alright, so that wasn't too bad, right? We've seen worse things in our math career. There's some questions coming up on worksheet 13 where they're not quite as simple. You know, I think we have time for number 1. Let's go ahead and go back and look at number 1. Again, I'm not going to worry about the limit business. Let's ignore that totally for today. Alright, let's identify some things. So right away I see a vertical asymptote at x equals 3. I don't see any holes in this graph. So we're on number 1 on worksheet 13 still. There seems to be some obliqueness happening over here. Let's not worry about that for this problem. What else did they tell us? Right here, there is a bounce at 4. So you do have an x-intercept at 4, but because it bounces, what kind of multiplicity are we going to see? Multiplicity of 2. Very good. And then right here, again, this should have been clearly labeled for you, but it's not. So you would have an x-intercept at -3, but again, it's going to bounce. So you have to remember that there's multiplicity of 2 there. All right, now this is something I do not expect you guys to know, and actually it's one of those things I had to look up when I first had to teach this class because I couldn't remember the rule. If on your vertical asymptote, if the end behaviors go up towards the same direction, like we don't usually see where they both go up and up. Usually one goes up and one goes down. When this occurs, that means your vertical asymptote has a multiplicity factor as well. So your vertical asymptote at x equals 3 is the factor x minus 3, but because it has like both infinite and behaviors, this factor has to show up twice. Again, that's nothing I need you to remember for testing. It's just something to note. Thank you. All right, right now. So then your X-Intercepts, which are at -3 and 4, those are factors from your numerator, but remember they're bouncing. So x plus 3 squared. Oh, sorry. And then x minus 4 squared. So we have something missing from this question. The fact that there is probably some sort of oblique asymptote happening because it is top heavy. Here's the question. Is there some factor in the front? Yeah, there is. Do you know what it is? No, you do not. So right now, we're going to call it k. But if you don't have a pencil, don't write that down. Because we're going to erase k in a minute. There's one more clue they gave you in this problem, and it's right here. It said it goes through the ordered pair 0, 24. Now, that is a y-intercept, and that does mean something to me when I'm in standard form, but guys, we are far from standard form right now. So what I'm going to have you do is I'm going to have you plug in a 0 for all the x's and a 24 for the y. So instead of y equals all this mess, let's set up 24 equals, leave k as a constant. This is one of those we don't know it yet things. And then every time you see an x, I need you to replace it with a 0. And every time you see, well, we only saw the y once, didn't we? Never mind. All right, so these are all zeros. You had a +3, you had a -4, and we had a -3 right here. So after doing a little simplifying, this is a 9 times a 16. Oh boy, we're going to have trouble here. 9 times 16 over, oh, I guess that's fine. This turns out to be a 9. So the 9s will cancel, and you get 24 equals k times 16. Y'all divide by 16 and reduce that fraction for me. And tell me, what did you just find out for k? Does it reduce to 3/2? Okay. So k, we just found out, whoops, that's not the ink. K is 3/2, which means this random constant that I just get to tack on to the beginning of my function is 3/2. Oh, that was a hoot. Yeah, I'm not going to test you on those. But this is a good warm-up for what we're going to do next on our lesson. Okay, put worksheet 13 aside. We'll try to finish it up maybe tomorrow. And then could you please find worksheet 14? And I believe we're on the back of worksheet 14. So remember, on worksheet 14 on the front, we are doing polynomial inequalities, and we had the graphing approach, we had the sign chart approach, and then we kind of were able to hybrid those two approaches. And I think that's what we'll take on here today. I'll show you kind of a hybrid of the two methods. Here's what I've determined after working with both classes on the first part of the lesson. I was remembering that some of you have a lot of trouble with coming up with the domain intervals. So I think, with that in mind, doing a hybrid approach and still doing the sign chart might help those of us who struggle with domain intervals to actually get them in the right notation and the right order. So I'm still going to graph it, still going to do a sign chart, maybe just not full out on either method. All right, ignore that. Here's the idea for a rational inequality. So you're going to have rational equations. Your rational inequality, the first thing is that you have to write it in general form. What that means is you need to write it so it's one massive fraction, which means we might have to get common denominators before we do any other work, because all of your knowledge about rational functions is based on what we call the general form of a rational, which is polynomial divided by polynomial. So that's kind of the bad news. Like, for instance, on this question, this was not in rational form. So if this was our question, we'd have to get common denominators. So we'd multiply this side by x plus 1 and this fraction by x minus 6. And after we simplified it, then we could go to town finding all the things that would create sign changes. She uses the word critical values here, and this is a good note. I think on your notes, which starts maybe right here, it says that you must include zeros of both the numerator and the denominator, because any points of discontinuity or a 0. So if you want a shorthand way of saying that, numerator and denominator equal to 0. Those would be all of your critical values. So if you think back to some of our rational functions, that could be a lot of things. So we got to keep that in mind. What we're going to do, because they do really encourage the sign chart in your textbook, we're also going to approach it from a graph. Now remember, my graphs are always ugly, even on a good day. And the good news is you don't need a really amazing graph. Plus you do have a graphing calculator. These are not the kind of questions that I would ever ask you to do without a graphing calculator. So this first question is already done for you guys. Notice they worked by getting a common denominator. Notice the original denominator was x minus 4 and the second denominator was x plus 1. So they multiplied both fractions by the missing parts, simplified, and came up with a new rational function in what we call general form. So then they found their critical points by setting everything equal to 0, because not only x-intercepts could be sign change areas, but also vertical asymptotes. We've seen where like the branch was above the axis on one side and then below the axis on the other side. So we got to keep that in mind. All right, so notice what they did here, guys. If they set the numerator equal to 0, they got x equals 2/3. And then when they set the denominators equal to 0, they got x equals 4. And x equals -1. So if you were doing strictly the sign chart method, what you would do next, and they already did this for you, I believe, on your paper, is they would write these critical points in number line order. So -1 would be first, and then 2/3, and then 4. And then you'd have to go through and test. Oh, thank you. So now we'd have to test, and this is where Abruzzo fails, because like the odds of me getting through each one of these test points without making a mistake is not real great. So if you're really good at testing points and evaluating functions, then go ahead and keep going with the sign chart method. But here's what I would do. I would either use my graphing calculator, or I would sketch something out real fast, and I would look at the graph. So you know what I need is I need more space. Let's pretend I didn't have a graphing calculator with me. So when I go back and look at my rational function, I see that we have vertical asymptotes at 4 and at -1. So I'd kind of do one of these. Okay, you got a vertical asymptote here, you got a vertical asymptote here. This is -1, this is 4. And then we have an x-intercept at 2/3. So I'm just going to pretend this is 2/3. And then you guys would not be expected to know what the graph looks like. So at this point, you would have to use a graphing calculator, okay? I'm not going to make you do this by hand. So you'd go peek at your graphing calculator and you'd recognize, you know what, another thing we didn't talk about though was where the horizontal asymptote was. Can you tell this one's bottom heavy? Because it's x over x squared. So there's a horizontal asymptote here at 0. While you're kind of sketching things out, it doesn't hurt to go ahead and write that down. So this branch does one of these. And then this part of the curve comes through. Whoops, that's ugly. And then this branch up here looks like this. So go back to the original problem. What do they want to know about your rational function? They want to know when it is greater than 0. Translate that for me. Positive, right? Positive. So this part is positive. Whoops, wrong color. This part is positive. Except what happens at 2/3 is it's equal to 0. So are you going to be able to count that? No. And then this part is positive. So to write that as an interval, what you'd have to say is, and this is hard for kids to understand, anytime it's a vertical asymptote, you always have to use a parenthesis because it's an asymptote. It's a discontinuity, and therefore you don't have any points there. So the green parts start at -1 and then go to 2/3. You're using a parenthesis because it doesn't say equal to 0. And then union, it starts up again at the next asymptote, so parenthesis 4, and then it continues to be positive above the x-axis for the rest of the The domain. Okay, that was a super fun time, wasn't it? Yeah, happy Halloween, everybody. All right, so here's what I will tell you. Here's my advice. Since you're probably going to be typing this on your calculator at some point, it would be very smart if you typed the original problem from one side of the inequality into y equals as opposed to your manipulated side. Can anyone predict why I might suggest that? Because what would happen if you made a mistake getting common denominators? You'll just be trusting your math when you go to use your answer, and then you're like, yeah, I totally have a vertical asymptote at 4. But what if you did something wrong? This would be a good way for you to check it. So the thing that I would type into y equals would be what happens to the rational once I bring everything to one side of the inequality. I'm still going to use this version to find my critical points, because that's the only version I know. But I'm going to verify what I'm finding algebraically with what I see on the graph. And I think that'll be a nice way for us to hybrid the two methods. Okay? So, that's already done. All right, number 5 is not done at all. So first of all, is this in general form? No, it's in like not even close to general form. So the first thing I'm going to do is I'm going to write x minus 1 over x plus 2, and I'm going to subtract the 3 over. And I'm going to make a little note to myself that this is the version that I'm going to type into my calculator. If you want, go ahead and type that into your calculator right now. So the only thing you got to be careful about, guys, is that the numerator and denominator have to be in a set of parentheses because they are more than one term. And then subtracting 3 out of the parentheses, obviously. So this is really going to be the hardest part for most kids. They don't like working with fractions, even in PreCalc. So you have to think about, okay, how do I get common denominators? Well, I look at my denominators, and I have an x plus 2, and I have a 1. So your least common denominator is going to be the x plus 2. The good news is the first fraction already has that. You do have to multiply the second fraction by an x plus 2 over x plus 2. So we're getting common denominators. We have, let's see, x minus 1 over here. And then be careful, you have a subtracting 3 that you're distributing into here. So you have a negative 3x and then a minus 6. So we have, oh boy, that's ugly, negative 2x minus 7 over the common x plus 2, and then I lost part of my inequality. Was this one greater than 0? Okay, so this is the question that we are going to algebraically test to find our critical points. So remember, guys, critical points would be anything that would make your numerator or your denominator equal to 0 today. So if you set your numerator equal to 0, you'd get negative 7/2. Okay. And then if you set your denominator equal to 0, you'd get negative 2. Now, those of you who aren't fans of fractions anymore, negative 7/2 is negative 3.5. You all just graphed it on your calculator, but remember which version you graphed? You graphed this version. Are you seeing something happening at negative 3.5? And does it look like it crosses the x-axis at negative 3.5? Because if it doesn't, then we've made a mistake. No, we haven't made a mistake, or no, it doesn't do anything. What? What did I do? Timeout. All right, so when I graphed it, and remember, in the y equals menu, I went back to the solved for 0 version, but the version before we got common denominators. I do see a vertical asymptote at negative 2, which makes sense because that was one of my other critical points, right? That was the denominator equal to 0. And then I believe it does cross here at negative 3.5. If you don't believe me, you could hit trace and then type negative 3.5 and see what happens. Yep, it's a 0. So here's where it's up to you guys. If you want, You can stick to the sign chart with the graphing calculator, or you can sketch yourself something. Now these being your notes, I think it might behoove you to actually give yourself a little sketch. So we have negative 3.5 first, and then you have a negative 2. It doesn't have to be a good sketch, obviously, since I'm doing it. But we have this vertical asymptote here at negative 2. It crosses the x-axis at negative 3.5, and it looked something like this, right? I forgot what this one was. It was... Oh, it's got a horizontal at negative 2. Wait, what? Oh, it's up! Oh, man. I have such a goldfish memory today. I know. Okay, you know what? There's no way I'm going to remember what you just told me. So let me just go back to my picture. Yep, totally looks like that. Alright, oh, because the horizontal's at negative 2. Ha 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 ha. Got it. So this is looking like this-ish, kind of. And then I already forgot what the other branch looks like. Someone help me out. Let's see. Okay. So it approaches from underneath the horizontal asymptote, which makes sense since you don't have any more x-intercepts. So this number right here, this is the negative 3.5. So when they're asking where your function is greater than 0, first of all, translate for me. Greater than 0 means positive. So I'm looking for all the positive parts. So that would be this guy. And that's kind of it. That is the only place where this function has a positive output. So 4.5 years later, we have our answer of it is positive starting where? At negative 3.5. You can say negative 7/2 if you want. Am I using a bracket or a parenthesis? Parenthesis, very good. So I'm going to go back to my fraction. Negative 7/2. And then this is kind of weird. It's not that it like stops being positive. It's just that the domain interval stops at negative 2. With a parenthesis because it's an asymptote. Therefore you can't be there. So that's your solution. Fun. Okay. Let's look at number 6. So right away I go, oh bummer, it's not in either of the forms. It's not graphing calculator friendly, nor is it in algebra friendly mode. So I'm going to do x plus 2 over x minus 4. We're going to subtract the 1 over and say less than or equal to 0. This is the version that we will type into our calculator. So I'm going to pause the video. Viewers are also going to pause so they can get their stuff entered. So we're not quite in that general form we need for our algebra moves, but this is good for graphing. And I do see a beautiful function. And we'll determine what all the important critical points are once we get the algebra ready for us. So we're going to go back to our paper. We're going to take this not general form rational and get it into general form by getting common denominators. So common denominators for this question would be an x minus 4. So the x plus 2 over the x minus 4 doesn't have to have anything multiplied by it, but you're going to need to multiply this fraction, which is 1 over 1, by x minus 4. So your common denominator is x minus 4, but up in this numerator, you have negative 1 times x minus 4, so you have negative x and then a plus 4. Now I kind of noticed when I was graphing this that there was no x-intercept that I could see. So let's look at the algebra and see how this shakes out. The x's do cancel in your numerator and you get a 6 over an x minus 4. So there's only one critical point, algebraically speaking, and that is at x equals what? X equals positive 4. The vertical asymptote is the only thing that could change sign. So when I go and look at my graph, yeah, that's what I'm confirming. And remember, we're always graphing the not quite general form one, just in case we made a mistake. They want to know where your function is, oh boy, this is ugly, where your function is less than or equal to 0. So you have this vertical asymptote here at 4. Is it like this? Do I have the right shape this time? Oh good, look at me go. Woohoo! So less than or equal to 0 would be anything negative. So I think they're referring to this branch here. Now, is it ever going to hit 0? No, there's no x-intercept. It never touches the axes. So we're not going to be using any sort of brackets on this interval because it doesn't actually get to 0. This is a vertical asymptote, therefore you can never get to 4. So the interval for which it is negative would be from negative infinity to 4. So those of us who are challenged by interval notation, this is what I want to see you do. I want you to, on your critical point sign chart, I want you to show me, okay, at 4, that it's negative, it's below the x-axis, and then beyond 4, sorry, before 4 it's negative, beyond 4 it is positive. So if I'm looking for things that are less than or equal to 0, I'm looking for this domain interval right here, which is negative infinity to 4. Now it does get a little tricky about when do you use parentheses and when do you use brackets. You really have to focus on the signs and whether it's a vertical asymptote or whether it's a point. So these are really complicated. There's a lot of things you got to think about. Okay, well, there's good news, bad news in this next question. Good news is this version is ready to type in my calculator. So this is the version that I would type into Y1, but I still need you guys to help me build up the common denominator. So I'm going to let you type while I work to get the common denominator. Oh boy, got a little bit of work on this one. Oh, so your common denominator is x plus 2 and x minus 4. So each fraction is going to have to get multiplied by the missing factor. So this is easy. 1 times x minus 4 is x minus 4. And then plus 3 times x plus 2 would be 3x plus 6. So we're going to collect our like terms there. What do we have? Let's see, 4x plus 2. And then leave these factored always, x plus 2 times x minus 4. Okay. So as far as critical points go, you have 3 of them. If you were to set your numerator equal to 0, you'd get a critical point at negative 1/2. You know, you subtract 2, divide by 4. If you were to set your denominators equal to 0, you would get critical points at negative 2 and at positive 4. So just make sure they go in number line order in this next step. So let's see, negative 2 would come first, and then a negative 1/2, and then a 4. And then from here, I'm probably going to kind of cheat and go back to my graph. Now, all of these things that you found on your graph, did something happen at negative 2 and 4 that look like vertical asymptotes? Excellent. Does it look like it crosses the x-axis at negative 1/2? So you might want to make a note on your sign chart that this one is the x-intercept, but these guys are the vertical asymptotes, which means you will have to use a parenthesis on the vertical asymptote if you need to use that endpoint. And actually, I think we need to use parentheses everywhere here, guys, because look at this symbol. Does it say equal to 0? Nah. So you're not going to be able to use any of the endpoints. All right, here we go. Can you confirm on your graph for me? If you look to the left of the vertical asymptote for negative 2, is it positive or negative? What? Negative, thank you. And then in between negative 2 and 1/2, positive or negative? Okay. And then in between negative 1/2 and 4? Positive still? Okay. Oh, we lied, it's negative. Which makes sense, because unless it bounced, it would cross through the axes. Okay. And then on the other side of the vertical asymptote of 4? Positive. Okay. Cool beans. I do not have that one graphed, so you guys should be looking at your own graph right now. I want to know where your function is greater than 0. That's fancy talk for positive. So I'm looking for this interval and this interval. Okay, pen, come on. So our domain interval, starting from the left, goes from negative 2 to negative 1/2, union 4 to infinity. Notice parentheses on everything. The only time you will use a bracket on these intervals is if it says like greater than or equal to or less than or equal to, and you're referring to an x-intercept. So if neither of those things are occurring, then it's parentheses all the way. All right, I really want to get to number 8. I'm so glad we have time. All right, bad news. Not in calculator form, nor is it in general form. So for calculator form, the one we're going to type into y1, I'm just going to have you guys type 2x plus 1 over 3x minus 2, and then you're going to add that 1 over, and it's greater than or equal to 0. So finally, we're going to have some fancy work with X-Intercepts. This is the version you're typing into y1, though, so go ahead and type that in. And then I'm going to start working on getting common denominators. So the good news is getting the common denominator here is not real tough. You just need to multiply the 1 by a 3x minus 2 over 3x minus 2. So denominator of 3x minus 2. So that's going to be a vertical asymptote. And then your numerator, let's see, I should probably not skip a step here. 2x plus 1 plus 3x minus 2, which gives us 5x minus 1, yeah, over 3x minus 2. When is this greater than or equal to 0? So as far as critical points go, it would be when your numerator and your denominator come out to 0, because either place is a possibility for a sign change. So the numerator is 1/5. That's going to be your x-intercept. And the denominator is when x equals 2/3. That's going to be a vertical asymptote. Now this time we finally have a case where there's an equal to bar. So we have to keep that in mind when we get to our sign chart. Okay, so I'm relying on your guys' picture to help me out with this next part because I hate plugging numbers in. So make sure they're in the right order, guys. 1/5 is smaller than 2/3. You probably want to make a little note on your sign chart here that 1/5 is an x-intercept. So that means we're going to be using brackets here. And the 2/3 is a vertical asymptote, which means you'd have to use a parenthesis there. All right, tell me, before 1/5, before that x-intercept, are we looking at positives or negatives? Positives, okay. Between 1/5 and 2/3, so between the x-intercept and the vertical asymptote, it was negative. Excellent. Okay. And then after 2/3, it was positive. So go back to the question here, guys. It wants to know where your function was greater than or equal to 0. So that's very fancy for positive, but including 0. So you're giving it this interval, but remember we're using a bracket right here. And then a parenthesis on the asymptote to infinity. So final answer, 400 years later, from negative infinity, whoops, to 1/5 with a bracket. Union. Can't use 2/3, so you got to use a parenthesis, because that's a vertical asymptote to infinity. Woo! Super fun. All right, the good news is, with having a graphing utility, everything you find algebraically, you should be able to confirm for me through the graphing calculator. Are we all clear as to why I'm encouraging you to enter this version into your calculator as opposed to the algebraically enhanced version? Because I've done it, I know you've all done it, like you make one tiny mistake, but if you're using that mistake to find the next part of the question, then you're not going to catch your mistake, because it's all going to make sense algebraically if you use the wrong function. Alright, so now you guys, oh my gosh, I even gave you time to start. You have the rest of worksheet 15. So 6 through 10. I'm not requiring you guys to like sketch the graph on the homework, but I would definitely probably jot down a little sign chart, and of course I want to see the algebra from you guys getting the common denominators. Alright, good luck.